Far beyond the orbit of Neptune, in the frozen darkness of the outer solar system, a strange crimson world drifts silently through space. It is so distant that sunlight reaching its surface is faint and cold, barely illuminating the icy landscape below. This remote world is called Gonggong, one of the most mysterious dwarf planets ever discovered. Astronomers first noticed something unusual about it. Unlike most icy objects in the Kuiper Belt, Gonggong appears deep red, almost like a frozen ember floating in the darkness. That color is not paint or rock. It is the result of billions of years of cosmic radiation slowly altering the chemicals on its frozen surface. Over immense stretches of time, sunlight and energetic particles have transformed simple ices into complex organic compounds, staining the world with its distinctive crimson tone. Gonggong is enormous compared to most objects beyond Neptune, stretching more than 1,000 kilometers across and even hosting its own moon, Xiangliu. Yet despite its size, it remains incredibly mysterious. No spacecraft has ever visited it. Everything we know about this distant world comes from faint reflections of light captured by telescopes here on Earth. So what kind of world is Gonggong really? Why is it so red? And what secrets might be hidden beneath its frozen crust? Tonight, we travel into the deep outer solar system to explore this strange and distant planet. And if you enjoy calm journeys through space and cosmic mysteries like this one, consider subscribing to Theories Before Sleep for more quiet explorations of the universe. Far beyond the familiar planets of the inner solar system, past the orbit of Neptune, where sunlight grows faint and distant, a vast region of icy remnants stretches through space. This remote frontier is known as the Kuiper Belt, a wide disk filled with frozen worlds, ancient debris, and mysterious dwarf planets that formed during the earliest days of the solar system. Among these distant objects drifts a particularly intriguing world, one that astronomers now recognize as one of the most fascinating bodies ever discovered beyond Neptune. This world is Gonggong. Gonggong is a dwarf planet that orbits the Sun at extraordinary distances, often more than 6 billion kilometers away from Earth. At such distances, sunlight takes hours to arrive, and even when it does, it appears faint and weak compared to the brilliant light we experience on Earth. Temperatures here plunge to unimaginable extremes, often dropping below -200 degrees Celsius. In this frozen environment, substances that are gases on Earth become solid ice. Yet Gonggong stands out from the countless other icy bodies that populate the Kuiper Belt. Unlike most of these distant objects, which often appear pale or grey when observed through telescopes, Gonggong displays a striking reddish colour. Its surface reflects sunlight with a deep crimson tint, making it one of the reddest objects known in the outer solar system. This unusual colour has puzzled astronomers since its discovery and has raised important questions about what might be happening on its surface. The answer likely lies in chemistry shaped by cosmic radiation. In the distant reaches of space, icy surfaces are constantly bombarded by energetic particles from the Sun and from interstellar space. Over millions and billions of years, this radiation slowly alters the chemical structure of frozen materials. Methane, nitrogen, and other simple molecules trapped within the ice can break apart and recombine into more complex compounds known as tholins. Tholins are organic molecules that form when simple carbon-based substances are exposed to radiation in extremely cold environments. These compounds often appear reddish or dark brown in color. Scientists believe that Gonggong's distinctive crimson surface may be covered in these radiation-altered materials, gradually built up over billions of years. But Gonggong was not always known to astronomers. For most of human history, this distant world remained completely invisible to us. Its orbit lies so far from the Sun that even modern telescopes struggle to detect it. The story of Gonggong begins only recently, during the early 21st century, when powerful survey telescopes began systematically searching the outer solar system for new objects. In 2007, astronomers working at the Palomar Observatory in California discovered a faint moving point of light, slowly drifting against the background of distant stars. Careful analysis revealed that the object was not a star or galaxy, but something much closer, a body orbiting the Sun far beyond Neptune. At first, the newly discovered object was given the provisional designation 2007 OR10, a temporary scientific name used while astronomers studied its orbit and characteristics. For years, it remained known only by this technical label, even as scientists began to realize that it was much larger than originally expected. Measurements soon suggested that the object was enormous, possibly over 1,200 kilometers in diameter. That size placed it among the largest objects known in the Kuiper Belt, comparable to other dwarf planets such as Quaoar and Sedna. But there was still much uncertainty. Because Gonggong is so distant, astronomers cannot easily observe it in detail. Instead, they must rely on subtle measurements of reflected sunlight and infrared radiation to estimate its properties. By studying how much sunlight the object reflects and how much heat it emits, scientists can estimate both its size and the composition of its surface. These measurements eventually revealed something remarkable. The object appeared significantly darker than many other icy bodies in the Kuiper Belt. While worlds like Pluto and Eris reflect a large amount of sunlight due to their bright frozen surfaces, Gonggong absorbs more light and reflects less. This darker surface supports the idea that radiation-processed organic compounds may cover large portions of the dwarf planet. As astronomers continued studying the object, its orbit also revealed something interesting. Gonggong travels around the Sun in a highly elongated path that takes it far beyond Neptune, and then gradually brings it somewhat closer before swinging outward again. One complete orbit takes roughly 550 Earth years. That means the last time Gonggong occupied its current position in space, humanity had barely begun using telescopes. During this immense journey, Gonggong experiences extreme variations in sunlight and temperature. At its closest point to the Sun, known as perihelion, it receives slightly more warmth. At its farthest distance, called aphelion, the dwarf planet drifts even deeper into the cold darkness of the outer solar system. These long orbital cycles may influence the behavior of volatile ices on its surface. On worlds like Pluto, scientists have observed seasonal cycles in which frozen nitrogen and methane slowly evaporate when exposed to sunlight and then refreeze elsewhere as temperatures drop. Similar processes may occur on Gonggong, although its greater distance from the Sun means that these changes would unfold far more slowly. Understanding these cycles is one of the reasons astronomers are so interested in studying distant dwarf planets. Each of these worlds represents a preserved relic from the earliest stages of planetary formation. Unlike the inner planets, which have undergone extensive geological change, many Kuiper Belt objects have remained relatively unchanged for billions of years. Their surfaces and compositions may still reflect the conditions that existed when the solar system first formed from a cloud of gas and dust. Gonggong is particularly valuable in this regard because of its size. Large bodies have enough gravity to retain certain volatile materials that smaller objects lose over time. This means Gonggong may still preserve ancient ices and compounds that could reveal how chemical processes operated in the young solar system. Yet Gonggong is not completely alone in its distant orbit. In 2016, astronomers analyzing observations from the Hubble Space Telescope discovered that the dwarf planet possesses a moon. This small companion orbits Gonggong at a distance of several thousand kilometers, forming a binary system drifting together through deep space. The moon was later named Xiangliu, after a mythological nine-headed serpent from Chinese legend. This discovery was important for several reasons. First, moons allow astronomers to calculate the mass of the primary body they orbit. By measuring how long Xiangliu takes to complete one orbit around Gonggong, scientists can determine how strong Gonggong's gravitational pull must be. From this information, they can estimate the dwarf planet's density and internal structure. Early calculations suggest that Gonggong may be composed of a mixture of rock and ice. Its density appears higher than that of purely icy bodies, but lower than that of rocky planets. This indicates that Gonggong likely formed from material that contained both frozen water and heavier minerals. Understanding this composition helps scientists piece together the story of how objects formed in the Kuiper Belt. During the early solar system, countless icy fragments collided and merged, gradually building larger bodies through a process known as accretion. Some of these growing worlds became large enough to hold onto volatile substances like methane and nitrogen, shaping their future evolution. Gonggong appears to be one of the survivors of that ancient era. While many smaller objects were scattered away or broken apart during the chaotic gravitational migrations of the giant planets, larger bodies like Gonggong managed to remain intact. Today, they continue orbiting quietly in the distant outskirts of the solar system, preserving clues about those violent early times. But even now, much about Gonggong remains mysterious. Astronomers still do not know exactly how thick its icy crust may be, whether its interior contains liquid layers, or how its surface evolves over long periods of time. Observations remain limited by the immense distance separating this distant dwarf planet from Earth. To truly understand Gonggong, a spacecraft mission would eventually be required. Such a mission would need decades to reach its destination, traveling billions of kilometers through the outer solar system. Yet the scientific rewards could be extraordinary. Close-up images could reveal the dwarf planet's craters, valleys, and icy plains. Instruments could analyze its surface chemistry and search for traces of exotic frozen materials. Until that day arrives, Gonggong will remain a distant red world, a frozen relic from the dawn of the solar system, quietly circling the sun in darkness far beyond the familiar planets. And with every new observation, astronomers come one step closer to understanding this strange crimson dwarf planet that drifts silently through the cold frontier of space. When astronomers began studying Gonggong more closely after its discovery, they quickly realized that this distant world was not just another small object drifting in the Kuiper Belt. Its size, orbit, and unusual coloration hinted that Gonggong might belong to a rare class of bodies known as dwarf planets, worlds large enough for gravity to shape them into roughly spherical forms, yet too small to dominate their orbital neighborhoods like the 8 major planets. Understanding why Gonggong belongs to this category requires stepping back and looking at how planetary bodies form and evolve in the outer solar system. Billions of years ago, long before Earth had oceans or continents, the solar system existed as a vast rotating disk of gas and dust surrounding the young sun. Within this swirling disk, tiny grains of material collided and stuck together. Over time, these fragments formed larger and larger bodies, first pebbles, then kilometer-scale objects, and eventually worlds hundreds or thousands of kilometers across. Closer to the sun, where temperatures were higher, rocky planets formed from heavier materials like silicates and metals. But farther away, where temperatures dropped drastically, frozen compounds such as water ice, methane, ammonia, and nitrogen became abundant. These icy materials helped build the distant bodies we now find in the Kuiper Belt. Gonggong formed within this cold outer region. At first, it was likely just one of countless icy fragments orbiting the sun. But through repeated collisions and gradual accumulation of material, the object grew larger. Over millions of years, gravity pulled its mass inward, slowly shaping it into a rounder form. Once a body becomes large enough, gravity smooths out most irregularities, creating the spherical shape typical of planets and dwarf planets. Based on current estimates, Gonggong's diameter is roughly 1,200 to 1,300 kilometers, making it one of the largest objects discovered beyond Neptune that has not yet been visited by a spacecraft. While smaller than Pluto, it is still massive enough to qualify as a dwarf planet candidate. But size alone does not tell the full story. What makes Gonggong especially intriguing is the nature of its surface. Astronomers studying reflected sunlight from this distant world noticed something unusual in its spectrum: the pattern of light wavelengths reflected back toward Earth. Spectroscopy allows scientists to identify the chemical composition of distant objects by analyzing how different substances absorb and reflect light. When sunlight strikes the surface of an icy world, certain molecules absorb specific wavelengths, leaving distinctive signatures in the reflected light. Observations of Gonggong revealed evidence of frozen methane on its surface. Methane ice is not uncommon among large Kuiper Belt objects. Pluto, for example, also possesses methane frozen across parts of its surface. However, methane behaves differently depending on the environmental conditions of each world. Over time, solar radiation and cosmic rays gradually break methane molecules apart, creating more complex carbon-rich compounds. These newly formed substances, often referred to as tholins, accumulate slowly across the surface, forming dark, reddish layers. This process may explain why Gonggong appears so intensely red. Unlike Pluto, which has active geological processes that refresh parts of its surface with brighter ice, Gonggong may have fewer mechanisms to renew its outer layers. As a result, radiation-altered materials could accumulate for billions of years without being buried or replaced. The longer this process continues, the darker and redder the surface becomes. This deep crimson coloration places Gonggong among the reddest objects known in the Kuiper Belt, suggesting that its surface has experienced extremely long periods of exposure to radiation without significant resurfacing events. Yet scientists suspect that Gonggong's interior may be far more complex than its frozen exterior suggests. Large icy bodies can generate internal heat through several mechanisms. Radioactive elements within their rocky components slowly release energy as they decay. Additionally, gravitational interactions and past collisions may have produced heat during the early history of the object. If enough heat accumulated inside Gonggong during its formation, it might have melted portions of its interior ice. In some dwarf planets, such internal heating can create subsurface oceans, layers of liquid water trapped beneath thick outer shells of ice. Pluto and several large icy moons in the solar system are believed to contain such hidden oceans. Whether Gonggong once possessed a subsurface ocean remains uncertain, but scientists consider it a possibility. Even if liquid layers once existed deep inside the dwarf planet, they may have frozen long ago as internal heat gradually dissipated over billions of years. Today, Gonggong likely contains a rigid mixture of rock and ice, although deeper layers may still retain unusual structures formed during its early evolution. Clues about its internal structure may also come from studying its moon. Gonggong's companion, Xiangliu, is a relatively small object compared to its parent body, yet its presence offers valuable insight into the history of the system. Moons around dwarf planets can form through several possible mechanisms. One possibility is capture, where a passing object becomes trapped by the gravity of a larger body. Another possibility is co-formation, where the moon forms alongside the primary object during the same period of accretion. A third scenario involves giant impacts in which a massive collision ejects debris that later forms a moon. Pluto's moon Charon likely formed through such a collision, and scientists believe similar events may have shaped other dwarf planet systems. For Gonggong and Xiangliu, the exact origin remains uncertain. However, the orbit of Xiangliu suggests that the two objects may share a long and complex gravitational history. The moon circles Gonggong at a distance of several thousand kilometers, completing one orbit approximately every 12 days. By studying this orbit, astronomers can determine the combined mass of the system and refine estimates of Gonggong's density. Early measurements indicate that Gonggong is somewhat denser than pure ice, supporting the idea that its interior contains a substantial rocky component mixed with frozen water. The moon itself may also reveal important clues about the past. Xiangliu appears darker than its parent dwarf planet, suggesting that its surface composition differs significantly. This difference could reflect variations in how each body formed or evolved over time. If Xiangliu originated from debris produced by a collision, its material may come from deeper layers of Gonggong's interior. Alternatively, if the Moon formed independently and was later captured, its composition could reflect a completely different origin within the Kuiper Belt. Understanding these relationships is essential for reconstructing the history of the outer solar system. The Kuiper Belt is not just a collection of frozen debris. It represents a fossil record of planetary formation. Each dwarf planet and icy body preserves chemical and structural information from the era when the giant planets Jupiter, Saturn, Uranus, and Neptune migrated through the young solar system. During that chaotic period, gravitational interactions scattered countless objects outward, shaping the structure of the Kuiper Belt we observe today. Gonggong's orbit offers important clues about this ancient process. Its path around the Sun is highly elongated and inclined compared to the relatively flat plane of the major planets. Such unusual orbits often result from gravitational disturbances that occurred during the early rearrangement of planetary orbits. Neptune, in particular, played a crucial role in shaping the Kuiper Belt. As Neptune migrated outward billions of years ago, its powerful gravity interacted with nearby icy bodies. Some objects were pushed into new orbits, while others were captured into resonances. Stable orbital relationships, where the object completes a specific number of orbits for every orbit of Neptune. Although Gonggong is not currently locked in a strong resonance with Neptune, its orbit still bears the imprint of those ancient gravitational interactions. By modeling how objects like Gonggong move through space today, astronomers can reconstruct the long-term history of planetary migration. In this way, studying a distant dwarf planet becomes a window into events that occurred billions of years ago, long before Earth's continents formed or life appeared on our planet. Despite these advances, Gonggong remains one of the least understood large bodies in the solar system. Its immense distance makes direct observation extremely challenging. Even the most powerful telescopes see it only as a tiny point of light. Detailed images of its surface features, mountains, valleys, or impact craters remain beyond our current capabilities. Future telescopes may change that. The next generation of large observatories, both on Earth and in space, will possess far greater sensitivity and resolution. These instruments could analyze the surface chemistry of Gonggong in greater detail, searching for traces of exotic ices or organic compounds. They may also refine measurements of its size, shape, and rotation. Preliminary studies suggest that Gonggong rotates relatively slowly compared to many other dwarf planets. One possible explanation is that the gravitational influence of its moon gradually slowed the dwarf planet's rotation over time through tidal interactions. This type of tidal locking occurs throughout the solar system. Earth's moon, for example, always shows the same face toward Earth because tidal forces synchronize its rotation with its orbital period. Whether Gonggong and Xiangliu will eventually reach such a state remains uncertain, but tidal interactions could still influence their long-term evolution. All of these factors make Gonggong a fascinating object for planetary scientists. It represents a bridge between the familiar dwarf planets we know better, such as Pluto, and the vast population of distant objects that remain largely unexplored. Each new observation adds another piece to the puzzle of how these distant worlds formed, evolved, and survived for billions of years in the cold darkness beyond Neptune. And yet, even as telescopes continue to improve, Gonggong remains far away, a crimson world drifting silently through the outer solar system, carrying secrets from the earliest era of planetary formation. The outer solar system is a region where time seems to move differently. Out there, far beyond the warmth of the sun, change happens slowly. Ice does not melt and flow as it might on Earth. Winds do not reshape landscapes, and oceans do not erode coastlines. Instead, the surfaces of distant dwarf planets preserve the marks of events that occurred billions of years ago. Gonggong is one of these ancient worlds. Although we cannot yet see its surface in detail, scientists can infer many things about its geology and history through indirect observations. By studying the way it reflects light, the way it rotates, and the way its moon moves around it, researchers can slowly build a picture of what this distant red world might look like. One of the first questions astronomers asked after Gonggong's discovery was simple. What kind of landscape exists on its surface? On many bodies in the outer solar system, the most dominant geological features are impact craters. Throughout the early history of the solar system, countless objects collided with each other as planets and moons formed. These collisions left behind scars, circular depressions created when high-speed impacts blasted material away from the surface. If Gonggong's surface has remained unchanged for billions of years, it could be covered in an enormous number of craters. These craters might vary widely in size, from small pits only a few kilometers across to massive basins hundreds of kilometers wide. Each crater would mark a moment in the long and violent history of the Kuiper Belt, when icy fragments collided with one another in the darkness beyond Neptune. However, not all dwarf planets remain frozen in geological time. Pluto, for example, revealed a surprising amount of activity when NASA's New Horizons spacecraft flew past it in 2015. Instead of being completely cratered, Pluto displayed vast plains of smooth ice, mountain ranges made of frozen water, and complex patterns formed by the slow movement of nitrogen glaciers. These discoveries changed scientists' understanding of distant icy worlds. They demonstrated that even small bodies in the outer solar system can remain geologically active for billions of years. Internal heat, chemical interactions, and the behavior of exotic ices can reshape entire landscapes over time. Could Gonggong also have experienced similar processes? The answer remains uncertain, but several possibilities exist. One factor that influences geological activity is size. Larger bodies retain heat more effectively than smaller ones because their greater mass traps energy inside. With a diameter exceeding 1,000 kilometers, Gonggong may have been large enough to sustain internal heat for a significant portion of its history. If that heat melted internal ice early in its formation, the dwarf planet might once have contained layers of liquid water beneath its frozen crust. Such internal oceans are thought to exist beneath the surfaces of several icy moons in the solar system today, including Europa and Enceladus. Although Gonggong lies much farther from the Sun than these moons, Internal heat from radioactive decay could have created temporary liquid layers long ago. If liquid water once existed inside Gonggong, it might have driven geological activity. Water trapped beneath an icy crust can slowly push upward, creating fractures and ridges on the surface. When the liquid eventually freezes, it expands, forcing the surrounding ice to crack and deform. Over millions of years, this process can reshape entire regions of a planet or moon. The surface of Gonggong may therefore contain networks of fractures or ridges formed by ancient internal movements. Another possibility involves cryovolcanism. Cryovolcanoes are volcanic structures that erupt not molten rock, but extremely cold liquids such as water, ammonia, or methane. These materials can erupt onto the surface and freeze instantly, forming smooth plains or dome-shaped structures. Evidence for cryovolcanism has been found on several icy bodies in the solar system, including Pluto and some of Saturn's moons. If Gonggong experienced cryovolcanic eruptions in the past, its surface could contain frozen flows of water ice or ammonia-rich materials that once rose from the interior. These deposits might appear smoother or brighter than surrounding regions, creating contrasts across the dwarf planet's landscape. However, the deep red coloration of Gonggong suggests that radiation processing has played a major role in shaping its surface appearance. Over billions of years, cosmic radiation steadily alters the chemistry of exposed ice. Methane molecules break apart and recombine into complex carbon compounds. These compounds gradually accumulate in thin layers across the surface, darkening it and giving it a reddish tone. Because Gonggong lies so far from the sun, its surface receives very little energy that could remove or refresh these materials. On Pluto, seasonal cycles of sublimation, the process where ice turns directly into gas, can redistribute volatile substances and expose fresh ice beneath older layers. But Gonggong's greater distance means that such cycles may occur much more slowly, if they occur at all. This suggests that the red materials covering Gonggong may have built up continuously for extremely long periods. In some regions, the accumulation of these dark compounds could form thick coatings that obscure the original ice beneath. If an impact event were to expose deeper layers of material, the freshly revealed ice might appear brighter than the surrounding terrain. Such contrasts could create striking patterns across the dwarf planet's surface. Large craters, for example, might display bright interiors surrounded by darker red terrain that has been exposed to radiation for longer periods. Another factor influencing Gonggong's surface may be its rotation. Every planetary body spins on its axis, though the speed of that rotation can vary widely. Some worlds rotate quickly, completing a full spin in just a few hours. Others rotate slowly, taking days or even weeks to complete one rotation. Observations suggest that Gonggong rotates relatively slowly compared to many other Kuiper Belt objects. One possible explanation involves the gravitational influence of its moon, Xiangliu. Over long periods, tidal forces between two orbiting bodies can gradually slow their rotations. Energy is transferred between the rotation of the primary body and the orbit of its moon, eventually leading to more stable configurations. This process may have affected Gonggong's rotation over billions of years. A slower rotation could influence temperature patterns across the dwarf planet's surface. Areas facing the Sun would remain illuminated for extended periods, while the opposite side would experience long stretches of darkness. Although sunlight at Gonggong's distance is weak, these variations could still affect how volatile substances behave on the surface. Certain ices might slowly evaporate from sunlit regions and redeposit in colder areas, creating subtle changes in surface composition over time. These processes would operate extremely slowly compared to similar cycles on planets closer to the Sun. On Earth, seasonal changes occur over months. On Mars, they unfold over years. But on Gonggong, seasonal cycles tied to its long orbit around the Sun could take centuries to complete. Imagine a landscape where the same season lasts longer than the entire history of modern human civilization. Such immense timescales define life in the outer solar system. Because change occurs so slowly, Gonggong may preserve geological features that formed during the earliest era of planetary formation. Craters from ancient collisions, frozen flows of cryovolcanic material, and fracture systems created by internal stress could remain visible for billions of years. In many ways, Gonggong acts as a time capsule from the distant past. Each feature on its surface could tell a story about the conditions that existed when the solar system was young, when giant planets were migrating, when icy worlds were colliding, and when the outer regions of the planetary system were still forming. Unfortunately, for now, we can only imagine what those landscapes might look like. Even the most powerful telescopes cannot resolve detailed surface features on Gonggong from Earth. The dwarf planet appears as little more than a tiny point of light, drifting slowly through the star-filled sky. Yet astronomers continue studying that faint light with remarkable precision. By analyzing tiny variations in brightness as Gonggong rotates, scientists can infer whether its surface contains regions of different reflectivity. Slight changes in color can reveal the presence of methane, water ice, or complex organic compounds. With each new observation, the picture becomes clearer. Future telescopes may soon be able to detect more subtle details, perhaps identifying patches of brighter ice or areas where radiation has darkened the surface more strongly. Spectroscopic studies may reveal whether other frozen compounds, such as ethane or ammonia, exist on Gonggong's surface. Each discovery will bring us closer to understanding the geology of this distant world. Until then, Gonggong remains a red planet of the outer solar system, drifting silently through the darkness of the Kuiper Belt. A frozen landscape shaped by ancient collisions, cosmic radiation, and the slow passage of time. Gonggong does not travel through space alone. Like many large objects in the outer solar system, it is accompanied by a companion, a small moon that quietly circles it through the darkness of the Kuiper Belt. This moon is called Xiangliu, and its presence has become one of the most important clues scientists have for understanding the nature of Gonggong itself. Moons are incredibly valuable to astronomers. When a satellite orbits a planet or dwarf planet, its motion can be measured very precisely. From those measurements, scientists can calculate the gravitational pull of the larger body. Once the strength of that gravity is known, researchers can estimate the mass of the object and begin to understand what it might be made of. Without Xiangliu, determining the true nature of Gonggong would be far more difficult. Xiangliu was discovered in 2016 using the Hubble Space Telescope. Even with one of the most powerful telescopes ever built, the moon appeared only as a tiny point of light near Gonggong. Yet that faint speck revealed a surprising amount of information. The moon orbits Gonggong at a distance of roughly several thousand kilometers and completes one orbit in about 12 days. By tracking this motion carefully, astronomers were able to estimate the combined mass of the system. These calculations helped refine estimates of Gonggong's density, suggesting that the dwarf planet is composed of a mixture of rock and ice, rather than pure, frozen material. That combination is important. Pure ice bodies tend to be less dense and more easily shaped by impacts and internal changes. Objects that contain larger amounts of rock are heavier and may retain internal heat for longer periods of time. Gonggong's density indicates that it likely formed from a blend of materials in the early solar system, a mixture of water ice, frozen gases, and rocky minerals that gradually merged into a single world. But the relationship between Gonggong and Xiangliu raises another intriguing question. How did this moon form? In the solar system, moons originate through several different processes. Some are captured objects that wandered too close to a planet and became trapped by its gravity. Others formed from the same cloud of material as their parent planet, developing side by side during the earliest stages of planetary formation. A third possibility involves giant impacts. When two large bodies collide, enormous amounts of debris can be thrown into orbit around the surviving object. Over time, this debris can clump together and form a moon. Scientists believe that Earth's moon formed in this way, after a collision between the young Earth and a Mars-sized object more than 4 billion years ago. Similar collisions likely occurred throughout the outer solar system as well. In fact, Pluto's large moon, Charon, probably formed from such a giant impact. The collision would have blasted material into orbit around Pluto, eventually creating the moon we see today. Because Gonggong also has a moon, scientists have wondered whether a similar event might have occurred there. If Gonggong experienced a massive collision early in its history, fragments of icy material could have been ejected into space and later gathered together to form Xiangliu. However, the exact nature of the Gonggong-Xiangliu system suggests that the story might be more complicated. Observations indicate that Xiangliu is surprisingly dark compared to Gonggong itself. While Gonggong displays a deep reddish color, its moon appears even darker and reflects less sunlight. This difference hints that the two bodies may have different surface compositions. If Xiangliu formed directly from Gonggong's material after an impact, scientists might expect the surfaces of the two objects to look more similar. Instead, the differences raise the possibility that Xiangliu may have formed separately and later become gravitationally bound to Gonggong. In other words, it might have been captured. Capturing a moon is not easy, especially in the vast emptiness of the Kuiper Belt. For capture to occur, energy must somehow be removed from the passing object's motion so that it becomes trapped in orbit instead of flying past. In the early solar system, such captures may have been more common than they are today. The Kuiper Belt once contained far more objects than it does now, and gravitational interactions between them could have slowed passing bodies enough for capture to occur. Another possibility is that Xiangliu formed alongside Gonggong, but evolved differently over time. Radiation from the sun and cosmic rays can alter surface materials in complex ways. If the moon experienced different environmental conditions, perhaps because of variations in temperature or composition, its surface might have darkened more rapidly than Gonggong's. Regardless of how it formed, Xiangliu now plays a crucial role in shaping the dynamics of the system. The gravitational interaction between Gonggong and its moon gradually alters both bodies over time through tidal forces. These forces arise because gravity pulls more strongly on the sides of each object that face the other. On Earth, tidal forces from the moon cause ocean tides. But in planetary systems, tides can also influence rotation and internal structure. Over extremely long periods, tidal forces can slow the rotation of a planet or dwarf planet. The energy lost from rotation is transferred into the orbit of the moon, gradually pushing the satellite farther away. This process may be occurring slowly within the Gonggong system. If enough time passes, the system could eventually reach a state known as tidal locking. In such a configuration, each body always shows the same face toward the other. Pluto and Charon already exist in this state, where both objects remain locked together as they orbit a shared center of gravity. Whether Gonggong and Xiangliu will reach this configuration remains uncertain. The immense distances and long timescales involved mean that these processes unfold over millions or even billions of years. Still, the presence of Xiangliu gives scientists a rare opportunity. Many Kuiper Belt objects have no known moons, making it difficult to determine their mass or density. Because Gonggong does have a satellite, researchers can perform much more precise calculations about the dwarf planet's properties. These measurements help place Gonggong within the broader population of dwarf planets beyond Neptune. Objects like Pluto, Eris, Haumea, Makemake, and Sedna all share certain characteristics, yet each possesses unique features that reflect its individual history. Some have multiple moons. Others spin extremely rapidly. Some display bright reflective surfaces, while others appear dark and red like Gonggong. Studying these differences helps astronomers understand how the outer solar system evolved. During the early stages of planetary formation, the giant planets likely migrated from their original positions. As they moved, their powerful gravitational forces scattered countless smaller objects into new orbits. Some bodies were flung outward into the distant Kuiper Belt, while others were sent inward toward the sun. This chaotic period reshaped the architecture of the solar system. Dwarf planets like Gonggong are survivors of that ancient turmoil. Their current orbits carry the fingerprints of those gravitational disturbances. By studying them carefully, scientists can reconstruct the sequence of events that shaped our planetary system billions of years ago. The Gonggong-Xiangliu pair therefore represents more than just a distant curiosity. It is a window into the processes that govern planetary formation in the outer solar system. Processes that determined where planets formed, how they migrated, and how smaller worlds survived in the vast regions beyond Neptune. Despite these advances in understanding, the system still holds many unanswered questions. What does the surface of Xiangliu look like? Is it covered in craters like many small moons? Or has it experienced geological changes of its own? How different is its composition from Gonggong's? And what exactly happened during the early stages of their formation? Answering these questions may require future space missions. A spacecraft traveling through the Kuiper Belt could one day fly past Gonggong and Xiangliu, capturing detailed images and measurements that telescopes on Earth cannot provide. Such a mission would reveal the true shapes of these distant worlds, their surface features, and perhaps even their internal structures. Until then, Gonggong and its moon continue their silent journey together through deep space. Locked in an ancient gravitational dance, they drift slowly around the sun, two small worlds orbiting each other while carrying the secrets of a time when the solar system was young, chaotic, and still taking shape. Gonggong exists in one of the most remote regions of our solar system, a vast and mysterious realm known as the Kuiper Belt. This distant region begins just beyond the orbit of Neptune and stretches outward for billions of kilometers into deep space. Within this enormous disk lie countless icy objects, remnants left behind from the formation of the solar system more than 4.5 billion years ago. These objects range from small fragments of frozen rock only a few kilometers wide to massive dwarf planets that rival Pluto in size. To truly understand Gonggong, we need to understand the environment it inhabits. The Kuiper Belt is often described as the outer frontier of the solar system, but in reality, it is more like a cosmic fossil field. Unlike the inner planets where geological activity and atmospheric processes have reshaped landscapes again and again, many objects in the Kuiper Belt have remained almost unchanged since the earliest days of planetary formation. Their surfaces preserve ancient materials that existed when the Sun was still surrounded by a swirling disk of gas and dust. When the solar system first formed, this disk extended far beyond the current orbit of Neptune. Within it, icy grains collided and gradually stuck together, forming larger and larger objects. Over time, these fragments grew into kilometer-sized bodies, then into massive protoplanets, and eventually into worlds hundreds or even thousands of kilometers across. Gonggong formed during this chaotic period. At that time, the region beyond Neptune contained far more material than it does today. Thousands of large icy bodies may have been forming simultaneously, colliding, merging, and scattering through space under the influence of gravity. But this crowded environment did not last forever. The giant planets Jupiter, Saturn, Uranus, and Neptune began migrating through the young solar system. As they shifted positions, their powerful gravitational forces reshaped the entire outer region. Some objects were pulled inward toward the Sun. Others were thrown outward into distant orbits. Many were completely ejected from the solar system altogether, becoming rogue objects drifting through interstellar space. The Kuiper Belt we see today is only a small remnant of that ancient population. Scientists believe that more than 90% of the original material that once existed in the outer solar system has been lost. The objects that remain, Pluto, Eris, Makemake, Haumea, Gonggong, and thousands of smaller bodies, are survivors of that turbulent era. Gonggong's orbit tells part of that story. Unlike the nearly circular orbits of the major planets, Gonggong travels along a highly elongated path around the Sun. Its distance varies dramatically during its long journey, sometimes bringing it somewhat closer to the Sun before carrying it far back into the deep darkness of the outer solar system. One complete orbit takes roughly 550 Earth years. To put that into perspective, the last time Gonggong was in the same position in its orbit that it occupies today, the telescope had not yet been invented. Humanity had no knowledge of planets beyond Saturn, and the idea of dwarf planets in the distant Kuiper Belt would have seemed unimaginable. These enormous timescales make the outer solar system feel almost timeless. Seasons on Gonggong could last for centuries. Temperature changes occur slowly as the dwarf planet moves closer to or farther from the Sun. Even sunlight behaves differently there. At Gonggong's distance, the Sun appears more like an extremely bright star than the blazing disk we see from Earth. Despite this faint sunlight, it still influences the chemistry of Gonggong's surface. Many dwarf planets in the Kuiper Belt contain volatile substances such as methane, nitrogen, and carbon monoxide. These materials can freeze solid in the intense cold of the outer solar system, forming icy layers across the surface. But even at such great distances, sunlight can slowly cause these ices to sublimate, changing directly from solid to gas. On Pluto, this process creates a dynamic cycle in which frozen nitrogen evaporates from sunlit regions and later refreezes elsewhere. On Gonggong, similar processes may occur, though they likely unfold much more slowly due to the weaker sunlight. If methane ice exists across Gonggong's surface, as observations suggest, it could gradually sublimate when exposed to sunlight and then redeposit in colder regions. Over centuries or millennia, these cycles might subtly reshape the distribution of ices across the dwarf planet. But sunlight is not the only force acting on Gonggong's surface. Cosmic radiation constantly bombards the outer solar system. High-energy particles from the Sun and from distant supernova explosions travel through space, striking exposed ice on the surfaces of Kuiper Belt objects. When these particles collide with frozen molecules, they break chemical bonds and trigger new reactions. Over time, simple molecules such as methane transform into more complex organic compounds. These compounds, called tholins, are responsible for many of the reddish colors seen on distant, icy worlds. They form thin coatings across surfaces, gradually darkening the ice beneath them. This process likely explains the deep crimson hue of Gonggong. Because the dwarf planet is so far from the Sun, there may be few mechanisms capable of removing these radiation-altered materials. As a result, the reddish layer could continue accumulating for billions of years, slowly turning the surface darker and darker. The longer the exposure continues, the more dramatic the color becomes. In some areas, thick deposits of these organic materials could hide the underlying ice entirely. Only fresh impacts, when a meteorite strikes the surface, might expose brighter ice beneath the dark layer. If we could observe Gonggong up close, we might see bright patches inside impact craters, where newly exposed ice reflects more sunlight. These contrasts between dark red plains and bright icy regions could create striking patterns across the dwarf planet's surface. Understanding these processes is important because Gonggong is part of a much larger population of distant objects. Astronomers have discovered thousands of Kuiper Belt objects, and new ones continue to be found each year. Some are only a few kilometers across, while others approach the size of small planets. Each of them preserves clues about how the solar system formed and evolved. Yet Gonggong belongs to a particularly interesting group within this population. Its size places it among the largest known bodies beyond Neptune. Only a handful of objects, Pluto, Eris, Haumea, Makemake, and Sedna, are known to rival it in scale. These worlds represent the largest surviving fragments from the original outer disk of material that surrounded the Sun. Studying them helps scientists answer fundamental questions. How did the giant planets migrate to their present positions? Why do some dwarf planets have moons while others do not? What chemical compounds existed in the early solar system? And how did these materials evolve over billions of years in the cold darkness beyond Neptune? Gonggong contributes valuable data to these investigations. Its unusual orbit, its deep red surface, and its moon Xiangliu make it a unique object among Kuiper Belt worlds. Each of these features provides clues about the dwarf planet's past and the environment in which it formed. But perhaps the most fascinating aspect of Gonggong is how little we still know about it. No spacecraft has ever visited this distant world. Every piece of information we possess comes from faint signals of light detected by telescopes millions or even billions of kilometers away. Yet those faint signals carry remarkable detail. From them, astronomers can determine the object's orbit, estimate its size, identify chemical compounds on its surface, and even detect the presence of a moon. Each new observation expands our understanding slightly further. Future telescopes, such as the next generation of giant observatories currently being built on Earth, may soon reveal even more. These instruments will have the ability to analyze the light from distant objects with unprecedented precision, allowing scientists to detect subtle variations in surface composition. Such studies could confirm whether Gonggong's surface contains methane, ethane, ammonia, or other frozen compounds. They might even reveal whether the dwarf planet has regions of freshly exposed ice that differ from the darker surrounding terrain. Until then, Gonggong continues its slow journey through the Kuiper Belt, orbiting the Sun once every half-millennium. A distant red world shaped by ancient collisions and cosmic radiation, drifting silently through the frozen frontier of the solar system. Understanding Gonggong also means understanding the broader category of objects it belongs to, dwarf planets. These worlds occupy a fascinating middle ground within the solar system. They are not small asteroids, yet they are not large enough to dominate their orbital zones, like the major planets. Instead, they represent a unique class of bodies that reveal how planetary formation works on the edges of a solar system. The term dwarf planet itself is relatively new in astronomy. For many decades, Pluto was considered the ninth planet of the solar system. Discovered in 1930, it remained part of the official Planetary family for 76 years. But during the late 20th and early 21st centuries, astronomers began discovering more and more large objects in the distant Kuiper Belt. Some of these bodies were similar in size to Pluto, and one of them, Eris, appeared to be even slightly larger. These discoveries forced scientists to reconsider how planets should be defined. In 2006, the International Astronomical Union introduced a new classification system. According to this definition, a planet must meet 3 conditions. It must orbit the Sun. It must be massive enough for gravity to shape it into a nearly spherical form, and it must have cleared its orbital region of other large objects. Pluto met the first 2 criteria, but not the third. The Kuiper Belt around Pluto contains many other objects with similar orbits, meaning Pluto does not dominate its region of space. As a result, Pluto and several similar bodies were placed into a new category: dwarf planets. Gonggong appears to belong to this same class. Although it has not yet been officially confirmed as a dwarf planet, its size strongly suggests that gravity has shaped it into a roughly spherical form. Objects larger than about 800 to 1,000 kilometers typically have enough gravitational force to overcome the strength of their materials and collapse into round shapes. Gonggong's estimated diameter of more than 1,200 kilometers places it comfortably within that range. But while the definition of dwarf planets might seem simple, the objects themselves are incredibly diverse. Take Pluto, for example. When NASA's New Horizons spacecraft flew past Pluto in 2015, scientists were astonished by what they saw. Instead of a frozen, inactive world, Pluto displayed vast plains of nitrogen ice, towering mountains made of water ice, and glaciers slowly creeping across its surface. Some regions appeared almost completely free of impact craters, indicating that geological activity had resurfaced the area relatively recently. Other dwarf planets show completely different characteristics. Haumea, for instance, spins so rapidly that its shape has been stretched into a flattened oval. It also possesses a ring system and 2 moons, making it one of the most unusual bodies in the outer solar system. Makemake appears brighter than many Kuiper Belt objects and may possess a thin atmosphere under certain conditions. Eris, another large dwarf planet, follows an extremely distant orbit that carries it far beyond Pluto for much of its journey around the Sun. Gonggong fits somewhere within this diverse family. Like Pluto and Eris, it is large enough to retain certain volatile substances on its surface. These substances, such as methane, can freeze into solid layers under the extremely cold conditions of the Kuiper Belt. But Gonggong's deep red color suggests that its surface has experienced extensive radiation processing, creating complex organic compounds that darken the ice beneath. Another factor that makes Gonggong interesting is its rotational behavior. Every planetary body rotates around an axis, though the speed of that rotation varies widely throughout the solar system. Earth completes one rotation every 24 hours. Jupiter spins even faster, rotating once in less than 10 hours. Some dwarf planets rotate relatively quickly as well, but Gonggong appears to spin more slowly than many of its distant neighbors. Scientists believe this slower rotation may be connected to the gravitational interaction with its moon Xiangliu. Over long periods of time, tidal forces between the 2 bodies can gradually change their rotation rates. When a moon pulls on the surface of its parent planet, it creates slight bulges in the planet's shape. As the planet rotates, these bulges shift position relative to the moon, producing friction inside the planet's interior. This friction slowly drains energy from the planet's rotation. The lost energy transfers into the orbit of the Moon, causing subtle changes in the system. Over billions of years, these tidal interactions can lead to dramatic transformations. In some cases, the rotation of the planet slows enough that it becomes tidally locked with its moon. This means the same side of the planet always faces the moon, just as the same side of Earth's moon always faces Earth. Whether Gonggong will eventually reach such a configuration with Xiangliu is still uncertain. The distances involved and the relatively small mass of the system mean that tidal evolution occurs extremely slowly. Even after billions of years, the process may still be ongoing. Another intriguing question involves the internal structure of Gonggong. Dwarf planets often contain layered interiors composed of rock and ice. The rocky material tends to sink toward the center, forming a dense core, while lighter ice rises toward the outer layers. If enough heat existed during the object's formation, this differentiation could occur early in its history. The source of that heat would likely come from radioactive elements embedded within the rocky material. As these elements slowly decay, they release energy that warms the interior of the dwarf planet. In some cases, this heat can melt internal ice, creating temporary subsurface oceans. Several moons in the outer solar system, including Europa and Enceladus, are believed to contain such oceans today. On dwarf planets like Pluto, evidence suggests that liquid layers may still exist deep beneath the surface. For Gonggong, the possibility remains open. If internal heating once occurred, it might have produced geological activity early in the dwarf planet's history. Cryovolcanoes, volcanoes that erupt icy liquids instead of molten rock, could have transported material from the interior to the surface. Such eruptions might explain variations in surface composition across the dwarf planet. However, because Gonggong lies so far from the Sun, its internal heat may have dissipated long ago. Over billions of years, the interior would gradually cool and freeze, leaving behind a rigid mixture of rock and ice. If this happened, Gonggong today would be largely geologically inactive. Its surface would slowly accumulate impact craters and radiation-altered materials, preserving a record of events that occurred throughout the history of the Kuiper Belt. Even in this frozen state, Gonggong remains scientifically valuable. Each dwarf planet in the outer solar system represents a snapshot of the conditions that existed during planetary formation. By comparing these objects, Pluto, Eris, Makemake, Haumea, and Gonggong, scientists can identify patterns and differences that reveal how the solar system evolved. For example, variations in density help determine how much rock and ice each body contains. Differences in surface color reveal how radiation chemistry operates in extreme environments. Orbital properties show how gravitational interactions with Neptune shape the architecture of the Kuiper Belt. Together, these clues form a larger story about the origins of our planetary system. Gonggong may not yet be as famous as Pluto, but its importance in that story continues to grow. Each new observation provides additional pieces of information about a world that formed billions of years ago and has remained hidden in the outer darkness ever since. In many ways, Gonggong represents the frontier of planetary science. A distant red dwarf planet slowly orbiting the Sun, carrying with it the chemical fingerprints of the early solar system and the secrets of a time when planets were still forming in the cold outer reaches of space. Beyond the familiar boundaries of the planets we know well, the solar system begins to change character. The bright warmth of the inner planets fades. The giant worlds of Jupiter and Saturn fall behind, and even the distant orbit of Neptune becomes just another milestone along the way. Farther out, the sun grows dim, and the environment becomes quieter, colder, and far more mysterious. It is in this distant realm that Gonggong continues its slow and silent journey. Understanding Gonggong's place in the solar system requires looking at its orbit, because the path a world takes around the sun often reveals the story of how it formed and how it evolved. Unlike Earth or the other major planets, Gonggong does not follow a nearly circular orbit. Instead, it travels along a stretched and tilted path through space. This type of orbit is common among Kuiper Belt objects, but Gonggong's path is particularly dramatic. At its closest point to the Sun, called perihelion, it is still far beyond Neptune. At its farthest point, called aphelion, it moves even deeper into the outer darkness. This long elliptical path takes about 550 years to complete. To understand how unusual that is, consider that Pluto requires roughly 248 years to orbit the Sun. Neptune, the outermost major planet, takes about 165 years. Gonggong's orbit therefore unfolds on timescales that stretch across many human lifetimes. When Gonggong completes one orbit around the Sun, entire civilizations on Earth may rise and fall. But the shape of the orbit is only part of the story. Gonggong's orbit is also inclined, meaning it is tilted relative to the flat plane in which most planets travel. The major planets orbit the Sun in a fairly thin disk called the ecliptic plane because they formed from the same rotating disk of material. Many Kuiper Belt objects, however, travel on tilted orbits that move above and below this plane. This tilt suggests that gravitational disturbances occurred during the early history of the solar system. As the giant planets migrated through the young planetary disk, their immense gravity disrupted the paths of countless smaller objects. Some bodies were thrown inward toward the Sun. Others were flung outward into the distant reaches of the Kuiper Belt. Still others were completely ejected from the solar system, becoming interstellar wanderers. Gonggong is likely one of the survivors of that chaotic era. Its current orbit may preserve the imprint of ancient gravitational encounters that occurred billions of years ago. By modeling how objects like Gonggong move through space today, astronomers can reconstruct the sequence of events that shaped the outer solar system. These models suggest that Neptune played a particularly important role. When the solar system was young, Neptune may have formed closer to the Sun than it is today. Over time, interactions with other giant planets and the surrounding disk of debris caused Neptune to migrate outward. As it moved, its gravitational influence swept through the outer solar system like a cosmic plow. Objects caught in Neptune's path were pushed into new orbits. Some were captured into orbital resonances, where their orbital periods became linked to Neptune's. For example, Pluto is locked in a 3:2 resonance with Neptune, meaning Pluto completes 2 orbits around the Sun for every 3 orbits of Neptune. Gonggong is not in such a strong resonance today, but its orbit still reflects the gravitational reshaping of that ancient era. Studying these orbital patterns helps astronomers understand the structure of the Kuiper Belt itself. The Kuiper Belt is not uniform. Instead, it contains several distinct populations of objects. Some follow relatively circular orbits close to the plane of the solar system. Others travel on highly elongated or tilted paths. These different groups reflect the various ways in which objects were scattered and rearranged during planetary migration. Gonggong belongs to the population known as scattered disk objects or related distant bodies whose orbits have been strongly influenced by Neptune's gravity. These objects often have elongated orbits and large inclinations, suggesting that they were pushed outward during Neptune's migration and never settled into stable resonances. Because of this, Gonggong spends much of its time far beyond the main body of the Kuiper Belt. At its most distant points, it travels through regions of space where the Sun appears incredibly faint. Temperatures there drop to extremely low levels, sometimes approaching -240 degrees Celsius. In such an environment, even substances like nitrogen and methane remain frozen solid. But despite the cold and darkness, Gonggong's orbit still exposes it to subtle changes in sunlight over time. As the dwarf planet moves closer to the Sun during part of its orbit, slightly more solar energy reaches its surface. This small increase in warmth could cause volatile ices, such as methane, to sublimate very slowly. Over long periods, this process might release thin clouds of gas above the surface. However, because Gonggong's gravity is relatively weak compared to larger planets, these gases would not remain trapped for long. Most would eventually escape into space. This means any temporary atmosphere on Gonggong would likely be extremely thin and short-lived. Nevertheless, even these subtle processes can influence the chemistry of the surface. When methane molecules break apart under ultraviolet radiation, they can recombine into complex organic compounds that accumulate across the surface as reddish material. This process likely contributes to the deep crimson coloration that makes Gonggong so distinctive. The interplay between sunlight, radiation, and frozen chemistry may therefore shape the dwarf planet's appearance over time. Another fascinating aspect of Gonggong's orbit is the enormous distance separating it from Earth. At its closest approach, Gonggong remains billions of kilometers away. At its farthest distance, that gap grows even larger. Because of this immense separation, observing the dwarf planet is incredibly challenging. Even the largest telescopes see Gonggong as only a faint point of light. Astronomers must rely on subtle measurements to learn about it. They track its movement against the background stars to determine its orbit. They analyze the spectrum of reflected sunlight to identify surface compounds. They measure tiny variations in brightness to estimate its rotation. Every piece of information comes from carefully interpreting that distant light. Yet despite these challenges, observations have steadily improved over the past decade. The discovery of Gonggong's moon, Xiangliu, allowed scientists to calculate the system's mass more accurately. Spectroscopic studies revealed evidence of methane on its surface. Thermal measurements helped refine estimates of its size and reflectivity. Each of these discoveries adds another layer to our understanding. Future observatories will push these investigations even further. Extremely large telescopes currently under construction on Earth will be capable of analyzing faint objects in the outer solar system with unprecedented sensitivity. These instruments may detect subtle variations across Gonggong's surface, or identify additional chemical compounds frozen within its icy crust. They may also refine measurements of the dwarf planet's rotation and shape. Although these advances will deepen our understanding, one thing remains certain: Gonggong will continue its quiet orbit through the outer solar system for centuries to come. Long after our current generation of astronomers is gone, the dwarf planet will still be tracing its slow path around the Sun, carrying the memory of a time when the solar system was young and chaotic. Every orbit it completes is a journey across more than 5 centuries, a silent traveler drifting through the frozen frontier beyond Neptune, preserving the ancient history of our cosmic neighborhood. If we could travel to Gonggong and observe it up close, the experience would feel unlike standing on any world humanity has ever imagined visiting. The dwarf planet exists so far from the Sun that the entire environment is shaped by extreme cold, darkness, and silence. Even compared to Pluto or Neptune, Gonggong lies deeper in the solar system's frozen frontier. The Sun would look very different there. From Earth, the Sun dominates the sky, appearing as a blazing disk that warms the planet and fuels life. But at Gonggong's distance, often more than 6 billion kilometers away, sunlight becomes weak and distant. Instead of a bright disk filling the sky, the Sun would appear as an intense star, brighter than any other star, but still small compared to how we see it from Earth. Despite its faintness, that distant sunlight still shapes the environment. Every tiny bit of energy arriving from the Sun interacts with the frozen surface of Gonggong. Temperatures remain extraordinarily low, typically estimated to be around -220 to -240 degrees Celsius. At these temperatures, substances that are gases on Earth behave very differently. Methane, nitrogen, carbon monoxide, and even oxygen can exist as solid ice. The ground beneath your feet would likely be a mixture of water ice and frozen gases, hardened into a surface as solid as rock. In fact, in such extreme cold, water ice becomes incredibly strong, almost like granite. Mountains on icy worlds are often made of frozen water because it behaves like stone under those conditions. But Gonggong's surface may not look like the bright icy landscapes of some other distant worlds, because radiation from space slowly transforms simple molecules into darker organic materials. The dwarf planet may be coated with layers of reddish compounds. These materials accumulate over billions of years as cosmic radiation interacts with methane and other molecules trapped in the ice. The result could be a landscape tinted deep red or dark brown. Imagine standing on a frozen plain where the ground beneath you appears crimson, stretching toward a horizon lit by faint starlight. The sky above would be incredibly dark, far darker than any sky seen from Earth. Without an atmosphere to scatter light, the stars would shine with extraordinary clarity. Thousands upon thousands of stars would be visible, forming a dazzling canopy across the sky. one object would stand out among them. Gonggong's moon, Xiangliu, would appear suspended in the sky, slowly moving along its orbit around the dwarf planet. Depending on where you stood on the surface, the moon might rise and set over the horizon in a slow celestial dance that unfolds across many hours. Because Xiangliu is relatively close to Gonggong, it could appear quite large in the sky, perhaps similar in size to how Earth's moon appears from our planet. Yet the environment would be almost completely silent. Without a thick atmosphere to carry sound, even the faintest vibrations would not travel far. Footsteps would make no noise. Winds would not exist. The surface would remain still and motionless, except for occasional impacts from tiny meteoroids striking the ground. These impacts are one of the few forces that actively shape the surfaces of distant dwarf planets. Throughout the solar system's history, countless fragments of rock and ice have collided with planetary bodies. In the outer solar system, where geological activity is often limited, these impacts leave long-lasting scars. Gonggong's surface may therefore be covered in impact craters. Some of these craters could be enormous, stretching hundreds of kilometers across. Others might be small pits created by tiny objects traveling at tremendous speeds through space. Each crater would mark a moment in time when another fragment of the early solar system collided with the dwarf planet. Because erosion processes are extremely limited in such environments, many of these craters may have remained unchanged for billions of years. But impacts might also reveal something beneath the dark surface layer. If the reddish materials coating Gonggong formed slowly through radiation processing, then deeper layers of ice beneath them could be brighter. When a meteorite strikes the surface, it might excavate fresh ice that reflects more sunlight than the surrounding terrain. From orbit, such craters could appear as bright patches against a darker landscape. These patterns are seen on several other icy bodies in the outer solar system. On Pluto, for example, some regions display bright ice that contrasts sharply with darker areas enriched in organic compounds. Gonggong may display similar variations, though we cannot yet observe them directly. Another feature that could exist on Gonggong is fractured terrain. When large icy bodies cool over time, their interiors contract slightly. This contraction can place stress on the outer crust, causing cracks and fractures to form across the surface. If Gonggong once contained a subsurface ocean that later froze, the expansion of freezing water might have also forced the surface to crack. Such fractures could create long ridges or valleys stretching across the dwarf planet's crust. On icy moons like Europa, similar cracks form intricate networks across the surface. While Gonggong lies much farther from the Sun than Europa, the basic physics of ice and internal stress may still produce comparable structures. These features would offer important clues about the dwarf planet's internal history. Another fascinating possibility involves the behavior of volatile substances on the surface. Although Gonggong's temperatures are extremely low, the slow movement of the dwarf planet along its orbit may create gradual seasonal cycles. As the dwarf planet moves slightly closer to the Sun, certain frozen compounds might begin to sublimate very slowly. This process could release thin layers of gas above the surface. Because Gonggong's gravity is relatively weak, these gases would not remain for long. Most would escape into space. But during the brief period before they dissipate, they might form a temporary and extremely thin atmosphere. Such atmospheres have been observed on Pluto during parts of its orbit. If similar processes occur on Gonggong, they could influence how materials are redistributed across the surface. Gases escaping from warmer regions might refreeze elsewhere, gradually reshaping the distribution of ices over centuries. Even though these processes unfold incredibly slowly, they still represent dynamic changes occurring on a world billions of kilometers away. But perhaps the most remarkable aspect of Gonggong is how isolated it truly is. The dwarf planet travels through a region of space where distances between objects are enormous. Even other Kuiper Belt objects are typically millions of kilometers away. Collisions between large bodies are now extremely rare compared to the chaotic early days of the solar system. For the most part, Gonggong simply drifts through the darkness. Its journey around the sun is steady and predictable, guided only by gravity. Each year, it moves slightly farther along its immense orbit, tracing a path that will not repeat its current position again for more than 5 centuries. During that time, humanity may undergo extraordinary changes. Technologies may evolve. Space exploration may expand beyond the planets we know today. It is possible that future generations could launch missions capable of traveling to the distant Kuiper Belt. One day, a spacecraft might fly past Gonggong. Such a mission would transform our understanding of this distant dwarf planet. Cameras could capture detailed images of its landscape. Instruments could analyze the composition of its surface ice and measure the properties of its thin environment. We might discover mountains, plains, and craters shaped by billions of years of cosmic history. Until that day arrives, Gonggong remains a remote and mysterious world, a crimson planet of ice drifting in the silent outer darkness of the solar system, preserving clues about the ancient processes that shape the planetary system we call home. The farther scientists look into the outer solar system, the more they realize that objects like Gonggong are not just distant curiosities. They are keys to understanding the early history of our planetary system. Every dwarf planet in the Kuiper Belt preserves fragments of a story that began more than 4.5 billion years ago, when the solar system itself was still forming from a vast disk of gas, dust, and ice surrounding the young sun. In those earliest moments, the solar system looked nothing like it does today. Instead of clearly separated planets traveling along stable orbits, the region around the sun was filled with swirling material. Tiny grains of dust collided and stuck together, gradually forming larger clumps. These clumps became rocks. The rocks merged into kilometer-sized bodies, and eventually those bodies began growing into planetary building blocks. This process is known as planetary accretion, but the process was far from gentle. The early solar system was a violent environment where collisions happened constantly. Massive impacts shaped the surfaces of forming planets and moons. Entire worlds were shattered, and fragments of debris scattered across the young planetary system. The Kuiper Belt, where Gonggong now resides, is a surviving fragment of that ancient construction zone. Unlike the inner planets, which underwent extensive geological changes over billions of years. Many Kuiper Belt objects remained relatively untouched. Their cold environments prevented large-scale melting or atmospheric erosion. Because of this, they preserve materials that date back to the earliest period of planetary formation. Gonggong therefore acts as a fossil world. By studying its composition and orbit, scientists can reconstruct the conditions that existed when the solar system was still assembling itself. In many ways, these distant objects are like time capsules, storing chemical and physical evidence from a time long before Earth developed oceans, continents, or life. One of the most important aspects scientists examine is surface chemistry. The outer solar system contains a variety of frozen compounds that rarely exist naturally on Earth's surface. These include methane ice, nitrogen ice, carbon monoxide ice, ammonia compounds, and complex organic molecules created through radiation chemistry. Each of these materials behaves differently under extreme cold. For example, methane can freeze solid at the temperatures found on Gonggong. When exposed to ultraviolet radiation from the sun and energetic particles from space, methane molecules break apart and recombine into more complex carbon-based substances. Over long periods of time, this process creates reddish organic materials known as tholins. These tholins are believed to be responsible for the dark red appearance of several distant objects, including Gonggong. Studying these materials is important because similar chemical processes may have occurred throughout the early solar system. The same radiation chemistry that alters the surfaces of Kuiper Belt objects might also have influenced the formation of organic molecules that eventually contributed to the development of life on Earth. In this way, distant dwarf planets can provide clues about prebiotic chemistry, the chemical pathways that lead toward life. Another major scientific question involves the internal structures of dwarf planets. Even though these worlds are small compared to the major planets, many of them may still contain layered interiors. Denser rocky materials tend to sink toward the center, while lighter ice rises toward the surface. If enough internal heat existed early in their history, some dwarf planets might even have developed temporary subsurface oceans. Evidence from Pluto strongly suggests that such oceans may exist. Data from the New Horizons mission revealed geological features indicating that Pluto's crust may float above a deeper layer of liquid water mixed with antifreeze compounds like ammonia. If Pluto could maintain such an ocean despite its enormous distance from the Sun, scientists wonder whether other dwarf planets might have experienced similar conditions. Gonggong's size makes this possibility particularly interesting. Objects smaller than about 400 kilometers rarely generate enough internal heat to melt large amounts of ice. But bodies larger than 1,000 kilometers, like Gonggong, may retain heat from radioactive decay within their rocky components. This internal heat could potentially melt ice beneath the surface, forming temporary liquid layers early in the dwarf planet's history. Over billions of years, these oceans would likely freeze as heat escaped into space, but the process of freezing could leave behind fractures, ridges, and other geological features on the surface. If Gonggong once possessed such internal oceans, traces of that ancient activity might still be preserved today. Another clue about the dwarf planet's history comes from its density. by studying the motion of its moon, Xiangliu. Scientists can estimate the mass of the system. Combining that information with measurements of Gonggong's size allows researchers to estimate its density. Current estimates suggest that Gonggong contains both rock and ice. This combination implies that the dwarf planet formed from a mixture of materials in the early solar system. Some of those materials likely originated closer to the Sun before being scattered outward by the migration of the giant planets. This mixing of material across vast distances was a key feature of early planetary evolution. When Jupiter, Saturn, Uranus, and Neptune moved through the young solar system, they disrupted the orbits of countless smaller objects. Some bodies were pushed outward into the Kuiper Belt, while others were thrown inward toward the Sun. This chaotic period of planetary migration shaped the structure of the solar system we observe today. Gonggong's orbit likely reflects this ancient process. Its elongated path and orbital tilt suggest that it was once influenced by gravitational encounters with Neptune or other massive bodies. These interactions may have pushed it into the distant orbit it follows today. By modeling these orbital histories, scientists can reconstruct how the giant planets moved during the early solar system. These models have become increasingly important for understanding why the solar system is arranged the way it is today. For example, Neptune's migration likely explains why the Kuiper Belt contains several distinct populations of objects. Some bodies were captured into stable resonances with Neptune, while others were scattered outward into more chaotic orbits. Gonggong belongs to the group of objects whose orbits were strongly altered by these gravitational interactions. Each dwarf planet in this region therefore acts as a piece of a much larger puzzle. By comparing their orbits, sizes, compositions, and surface properties, astronomers can test theories about planetary formation and migration. Observations of Gonggong contribute directly to this research, helping scientists refine models of how the solar system evolved. But despite all these advances, Gonggong remains one of the least explored large bodies in our planetary neighborhood. No spacecraft has ever visited it. No images exist showing its surface in detail. Everything we know about it comes from distant telescopic observations, yet those faint observations are still incredibly valuable. Every new measurement helps scientists refine their understanding of this distant dwarf planet. Improved telescopes allow astronomers to detect subtle variations in reflected light that reveal chemical compounds on the surface. Infrared measurements provide clues about temperature and thermal properties. Precise tracking of Gonggong's motion improves estimates of its orbit and long-term stability. These studies gradually transform a distant point of light into a real world with its own physical properties, history, and environment. But perhaps the most exciting possibility lies in the future. Humanity's exploration of the solar system has steadily expanded outward. Spacecraft have visited Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, and many of their moons. Each mission has revealed landscapes and environments that once existed only in the imagination. The Kuiper Belt remains one of the last unexplored frontiers. If future space missions venture deeper into this distant region, Gonggong could become a potential target. A spacecraft passing near the dwarf planet could capture detailed images of its surface, measure its chemical composition, and study the dynamics of its moon. Such a mission would transform our understanding of this mysterious red world. Until that day arrives, Gonggong continues its slow orbit through the outer solar system, an ancient relic drifting through the darkness, preserving secrets from the earliest era of planetary formation. Gonggong is one of the newest worlds in our awareness, yet it is also one of the oldest worlds in existence. Long before Earth formed oceans, long before the continents shifted into their modern shapes, and long before life appeared on our planet, Gonggong was already drifting through the outer solar system. It has traveled along its distant orbit for billions of years, silently circling the Sun, while the rest of the solar system changed and evolved. That alone makes Gonggong remarkable. In the vast history of our planetary system, most objects did not survive unchanged. Many were destroyed in violent collisions. Others were scattered into interstellar space when the giant planets shifted their positions. Entire populations of early objects vanished during those chaotic early epochs. Yet Gonggong endured. It survived the era when Jupiter and Saturn migrated through the early solar system. It survived the gravitational disturbances caused by Neptune moving outward into the Kuiper Belt. It survived billions of years of cosmic radiation and countless impacts from small fragments of ice and rock. And today, it continues its journey, largely unchanged, carrying with it a record of that ancient history. This is why astronomers find Gonggong so fascinating. Dwarf planets like Gonggong are not simply small and distant worlds. They are archives of the solar system's past. Their surfaces preserve chemical and physical evidence from the earliest stages of planetary formation. By studying them, scientists can investigate the processes that shaped our planetary neighborhood billions of years ago. Each observation adds another piece to the story. When astronomers first detected Gonggong in 2007, it appeared as nothing more than a faint point of light moving slowly against the background of stars. From that tiny signal, researchers began to extract information about its orbit, its size, and the nature of its surface. Over time, the picture became clearer. They discovered that Gonggong follows a highly elongated orbit that takes more than 5 centuries to complete. They identified methane ice on its surface and recognized that radiation from space had transformed parts of that ice into complex, reddish, organic materials. They found that Gonggong possesses a moon, Xiangliu, whose orbit allowed scientists to estimate the dwarf planet's mass and density. Each discovery brought Gonggong into sharper focus. But even today, much about this distant world remains unknown. We do not yet know what its surface truly looks like. Is it heavily cratered like many ancient icy bodies? Does it contain smooth plains created by cryovolcanic flows? Are there mountains formed from solid water ice rising above frozen plains of methane and nitrogen? We can only speculate. Even the best telescopes on Earth cannot resolve surface details on Gonggong. At such enormous distances, the dwarf planet appears as only a tiny dot of reflected sunlight. And yet, that distant light still carries extraordinary information. From subtle variations in brightness and color scientists can deduce the presence of specific molecules. They can measure how fast Gonggong rotates. They can track the orbit of its moon and calculate the strength of its gravity. These techniques transform a point of light into a world with measurable properties. But there is only so much that telescopes can reveal. To truly understand Gonggong, humanity would need to send a spacecraft into the distant Kuiper Belt. Such a mission would not be easy. Even the fastest spacecraft ever launched would require decades to reach Gonggong's orbit. The distance is immense, billions of kilometers beyond Neptune. A probe traveling there would need advanced navigation systems, reliable power sources, and instruments capable of studying a world in extreme cold and darkness. Yet missions to distant worlds have succeeded before. The New Horizons spacecraft, launched in 2006, traveled for nearly a decade before reaching Pluto in 2015. During its brief flyby, it revealed a world far more complex and dynamic than scientists had imagined. Glaciers of nitrogen ice flowed across Pluto's surface. Towering mountains of frozen water rose several kilometers high. Vast plains appeared almost completely free of craters, suggesting surprisingly recent geological activity. That mission transformed our understanding of dwarf planets. Before New Horizons, Pluto was thought to be a frozen relic of the early solar system. After the flyby, it became clear that even distant icy worlds can possess active geology and complex environments. Gonggong could hold similar surprises. Perhaps its surface contains landscapes shaped by ancient cryovolcanoes. Perhaps fractures and ridges reveal a past when internal oceans pushed against the crust. Perhaps regions of bright ice contrast with darker areas, rich in organic compounds created by radiation chemistry. Without direct exploration, we cannot know. But the possibility itself is exciting. Each new dwarf planet discovered in the Kuiper Belt expands our understanding of the solar system's diversity. Worlds like Eris, Makemake, Haumea, Sedna, and Gonggong remind us that the solar system is far larger and more complex than we once believed. Even now, astronomers continue discovering new objects in this distant region. Large survey telescopes scan the sky night after night, searching for faint moving points of light beyond Neptune. With every new discovery, the known population of Kuiper Belt objects grows. Some of these objects may eventually prove to be dwarf planets themselves. Others may represent entirely new classes of bodies, worlds that challenge existing theories about planetary formation and migration. The outer solar system is still full of mysteries, and Gonggong stands among the most intriguing of them. It is a world defined by distance, by darkness, and by time. Its orbit spans centuries. Its surface has endured billions of years of cosmic radiation. Its chemistry preserves the record of ancient processes that occurred when the solar system was still forming. From Earth, we see only a faint red glimmer in the night sky. But behind that glimmer lies a frozen planet-sized body drifting through the Kuiper Belt, an ancient survivor of the early solar system, carrying secrets that scientists are only beginning to uncover. Perhaps one day, far in the future, a spacecraft will approach Gonggong and reveal its landscapes in detail. Until then, it remains a distant red planet of the outer solar system, orbiting silently in the deep cold beyond Neptune, reminding us how vast and mysterious our cosmic neighborhood truly is.